Alright, so let us proceed with our lesson 6, the last lesson for the preliminaries. So this is the Besout identity. By the way, Besout identity can only be solved if you are able to understand the Euclid's algorithm. Okay, so we need the Euclid's algorithm for us to be able to solve Besout identity. Now, before proceeding with the examples, let us first check what is Besout identity. So in elementary number theory, Besout identity is also called as Besout lemma. It is the following theorem. Let A and B be integers with the greatest common divisor D. Then there exist integers x and y such that ax plus by is equals to D. More generally, the integers of the form ax plus by are exactly the multiples of D. Okay, so for us to be able to understand more about Besout identity, let us also make sure to remember the 8 important facts of Besout identity. So let A and B be integers, not both 0. So one can either be 0 but not both. Okay? Then there are 8 important facts related to Besout identity. First is there is a greatest common divisor of A and B called GCD. And there is at least positive linear combination of A and B. Also, Besout identity, these two numbers are the same and it can be called G. So all common divisors of A and B are divisors also of G. Conversely, all divisors of G are common divisors of A and B. 6. All linear combinations of A and B are multiples of G. 7. Conversely, all multiples of G are linear combinations of A and B. Lastly, if D is a common divisor and E is a linear combination, then D is divisible to E. Now let us have here an example of Besout theorem. So, given that integers AB and GCD AB is equals to so then GCD AB is equals to AX plus BY, or the combination equation. Okay, so let us have here an example. Find the solution of Besout identity for A is equals to 5 and B is equals to 7. So let us find x, y, or the integers x to y, such that 7x plus 5y is equals to GCD of 7 and 5. Okay, so let's start with the step 1. Again, in the step 1, we will be doing or using the Euclid's algorithm. Now in step 1, since we have A is equals to 5 and B is equals to 7, so let's use 7 here equals to 5 times 1 plus 2. Then 5 is equals to 2 times 2 plus 1. And then 2 is equals to 1 times 2 plus 0. Now, since we are able to get the 0, so we have understood that the greatest common divisor here, or the GCD, is the 1. Okay? So, let's proceed with the step 2. Now, in step 2, the only thing that we need to do is reverse the Euclidean algorithm. So, we have here 1 is equals to 5 minus 2 times 2. So where did we get the 5? So this is in this particular equation, the second one, wherein we are able to get the GCD, which is 1. So 1 is equals to 5 minus 2 times 2. Now, for us to be able to get the second one, all we need to do is to copy the equation or the first equation. So as we already know, 2 is equals to 7 minus 5 times 1. So this is from this first equation. Now, if we solve this one, we will be able to get the second equation for the Besout identity. 1 is equals to 5 minus, let's copy the 7 minus 5 times 1 here, and then the 2, which is the equals in this particular equation. Then afterwards, if we solve this one, as you can see, we need to copy the 5 and then minus. It would be 7 times 2 plus 5 times 2, because if we multiply 7 times 2, that would be 7 times 2, and then plus, since it's 5 times 1, so it's 5 only, and then multiplied by 2, so that would be 5 times 2. So in here, let's solve on the next equation. So we need to actually, since there are 5 on both sides, so we need to transfer the 5. So we need to like copy first the negative 7 times 2 plus, as you can see, on the upper equation we have here 5 times 2 and another 5. So that means we have 3 5s. So that is negative 7 times 2 plus 5 times 3. Now, since the negative is in the number 7, we need to transfer it to the number 2. So if we transfer that one, that would be 7 times negative 2 plus 5 times 3. So again, we just transferred the negative, but it would still be the same calculation. So negative 7 times 2 will be negative 14, and 7 times negative 2 will be negative 14 still. Now if you will solve this one, 7 times negative 2 is negative 14 plus 5 times 3 is 15. So we will be able to get 1 as our answer. Meaning, if we change the x and y here as negative 2 and 3, and we will go back to the original formula, let's have here the step 3, which is the 7x plus 5y is equals to GCD 7 and 5. So we can see here that 1 is the GCD of the 7 and 5, just like what we've solved in the Euclidean algorithm, equals 7 is the first given number, or the a, x here is negative 2, and then plus 5 is the this is the a, 5, and the 7 is letter b. So 5 times 3, since our y is 3, if you solve this one, you will get 1 is equals to 1, meaning we are able to get the Besout identity. Alright? Okay, so that ends our discussion for preliminaries.